first thing to emphasize, and I mention this at every meeting I do, is additive manufacturing is just another process. So we need to make sure we don't treat it in a special way. The same rules apply, okay? It has some unique characteristics which we need to be aware of. So in the same way you need to understand about forging or casting or injection molding, you need to understand about additive manufacturing because it's quite complicated. So what does additive manufacturing offer? Well, it offers unrivaled geometrical freedom. So compared to lots of traditional manufacturing processes, we can make some really complicated parts. Now, complicated is not necessarily good, but it just gives you the option if you want to do it that way. Production flexibility. It allows you to make one off or maybe 1,000 off in the same way and in the same degree of economic viability. So it's very few manufacturing processes where one-off is a possibility. It's efficient use of materials. So many of you are familiar with machining parts from huge billets of metal. You know, in the aerospace sector, we often use the term buy to fly, and it might mean that at a one kilo component requires a 30 kilo billet to make it. That is not good news. So in terms of additive manufacturing, we can at least claim that it's an efficient process. And finally, there's material flexibility, which we haven't really used yet. But because we're laying down material in layers, we can pattern each layer potentially, and we can alter the composition as we move up the component. I'm just going to show you a little bit where the technology has evolved over the years. Most of you who've been in additive manufacturing have seen this change. It's taken a while. It's been almost 20 years in coming, but we're now at the destination which we all hope for. So initially, we had additive manufacturing being used for prototyping, for checking the design is okay, when CAD systems are really quite awful. Then we moved to fit and function, where we're trying to make sure that the part assembles, you can get all the wires in, the lid closes. Function testing, making sure that the actual part operates correctly, doesn't fail. Casting patterns, this is a very big application still, where we're making, for example, on the left, a stereolithography pattern, on the right, an investment casting. We're about to open a new centre in Coventry, and one of the primary areas is to take this technology and see it be used for high temperature, high performance aerospace parts. We've even tried to use additive manufacturing for tooling with varying degrees of success. Okay, it went in and out of favour. And finally, rapid manufacturing, making the end-use parts. And this is much more a convincing argument, in my opinion. So although all of those applications are important, the final application, the production of end-use parts, is by far the most important, in my opinion. I don't know how many people have used additive manufacturing for making end-use parts. I'm going to have a quick show of hands. How many people have used additive for making end-use parts? That's pretty good, that. That's about maybe almost half the audience. How many people had a successful experience? Yeah, not so good. About perhaps half of those people put their hands up. I think the jury's still out. Part of the reason for these slides is to show you some of our experience of trying to help companies navigate the journey into additive manufacturing. I think the first thing to bear in mind is get the mindset right. Don't be too conservative, i.e. don't make a washer, you know, but equally don't make a full car in aluminium or something. You know, it's not to take too many risks in this business because it's a new process and it's still being developed. Also, manage expectations. The media has not helped us very much in terms of managing the expectations of our senior managers. They think that we can print anything. It simply isn't true. I also would say that if it has gone wrong, learn from that experience. At the end of the day, other manufacturing processes go wrong too. You know, there's never, you know, most casting companies have castings that go wrong. It's not unusual. So there's a few facts and fictions. Additive manufacturing can transform businesses if used appropriately, but it is wrong to say it can be used for anything. Okay, that's very important. There is an assumption anything can be printed. It's simply not true. When you're starting this journey, look for the right sort of parts. Generally speaking, additive manufacturing suits complex, small components manufactured in low volumes. There are exceptions to that rule, but that's a pretty good yardstick to judge things. Some of the new additive manufacturing technology will alter that, but at the moment, stick to that rough rule of thumb. Select the right process. This is difficult. We have lots and lots of different processes. So just looking at metals parts alone, we have powder bed fusion processes, so laser melting, electron beam melting. They have different characteristics. Laser melting, precise but relatively slow. Electron beam, significantly faster, but you're getting a rather rough cast component-like. Directed energy deposition, cladding. I don't think there's many cladding examples at the show this week. So you can have wire feed and powder feed options. You can even take a powder bed and print a binder to produce green components. That's just the metal parts, not forget the plastics and ceramics. And then, having selected your process, you have to consider the actual characteristics of the particular machines. So if we look at laser melting machines, they're all roughly the same sort of process. Taking the powder, laying it down in a layer, and using a laser to fuse that powder. But each process has a subtle sweet spot that differentiates it from another machine. So I said it was going to be difficult. You know, if you're buying a machine, it's very difficult to choose exactly the right process. Another important factor is think about the design of the part. It is rare that if you have a part that is being machined or forged or cast, you can immediately use that design for additive manufacturing and make it a good result of it. It is best to design for the process, as you would do with conventional manufacturing processes. This is an important quote. I mean, GE are amongst the leaders in using additive manufacturing for production parts. And there's no point in having the capability to produce new shapes and then not use it. To me, it's not adding value to your business. And so you can see here that Steve Renger says, you can produce designs and components you could never do with traditional manufacturing processes. So why use the existing design if you've got the option to change it? So these are the opportunities that you've got. You can enhance the performance of the product. You can consolidate components together. You can part customize. So you've got a small volume application which is not commercially viable using conventional manufacturing techniques. This is an option for you. And finally, there's the aesthetics. I'm an engineer, not a designer, but apparently that's important if you're selling products. So here's an example. This is one you might see around the show. It's a heat exchanger designed entirely to be made by additive manufacturing in a single hit. Normally these things are produced and assembled and fused together, often by welding. It costs more to make it. Okay, this is going to be difficult for those guys in procurement. It costs more to make it this way, but what you do is you recoup the benefits when you use it. So this is going to require a little bit of sales within your organization to get this accepted. Lightweight performance. So you can see here on the left is an example of a part of a bicycle frame produced by laser melting from titanium. It is not cheap. There's no way it can be said it's cheap. But given the fact that some of us are buying carbon composite racing bikes that cost several £1,000s, maybe it has a market. On the right, we have an example from Paramount Industries, a lattice type component. You cannot produce that type of component by any other technique. Surface topology. So if you're into the medical sector, that's quite important. So here's an example of an acetabular cup. Okay, fits in the pelvis. It's produced by additive manufacturing, typically by electron beam melting. And it has this complex open lattice structure that allows the bone to grow into it. And that means the patient recoups quickly, the implant stabilizes, and there's less chance of the patient, the implant falling from the patient. Parts consolidation. You know, we're used to parts consolidation in things like injection molding and to some extent casting. But this is really important because if you have to assemble something, it costs money. It has to be checked. You need fasteners. It's usually heavier. This is an example from GE. It's the GE Elite fuel nozzle. 20 components into one component. It really shows what you can do if you design for the process. And finally, customization. The medical industry, as well as producing large volumes of parts, can also make patient-specific implants. Some of us are not the same size. I've been told I'm quite short. So the implant for me would have to be a different size than the implant, say, for Frank here. It's quite a big bloke. So this is a way of making sure we can get the right implant. And there's even a company now making implants for animals, for dogs. So there you go. As I say, I'm not a designer, I'm an engineer, but aesthetics are important. And here's a few examples. So on the top right-hand example, that's a light fitting, designed and sold through Magix, through Materialise. We have this example of a dress, and then finally we have the example of this watch. Now, later on, Frank will talk a bit about the use of additive manufacturing in jewellery. It has transformed the production of jewellery, and it's one of the biggest applications. You won't see it very often because it's not sexy like aerospace applications or Formula One, but it's very, very important. Material properties. The thing to consider is you're building parts in layers, and it does introduce slight differences between the properties in the build direction and across the build platform. Now those can be designed for as long as you're aware of them. So you end up with these anisotropic properties like you would have with composites, but not quite as bad. So as long as you consider them, it's fine. And they can be an advantage. So for example, if you have large columnar structures that tend to build in the Z direction, that tends to improve the fatigue properties of parts. In some cases, the properties of parts are better or equal to those that can be produced with traditional techniques. Not always, but in the case of metals parts produced by the selective laser melting or electron beam melting have properties which are closer to forging than they are to casting. Part surface finish. It's a bit of a pain. We don't get super smooth parts. They're typically similar to a sand casting in most cases. On the best machines, you might get an investment cast-like finish, but generally it's more like a precision sand casting. So that has to be considered. There's also this effect of stair-stepping. So if you have a shallow surface to the horizontal, you end up seeing each layer as you go along. It's not a problem as long as you cater for it when you design and you build a component. So in the worst state, you might have to build a machining allowance in for certain critical features. It's something we do in casting all the time, but the number of times I've seen parts being made and someone says afterwards, what about machining allowance? It's too late then, you've made the part. Part inspection. we're making parts in hundreds, if not thousands of layers. Unlike most processes, we've got 1,000 times chances to make a mistake. Any layer with a defect could be fatal for the operation of the part. So inspection is absolutely crucial. For many applications, 100% inspection of parts is required. This comes with a cost and also a time penalty. And in some cases, if you make a fancy lattice structure like this, it's quite hard to inspect. You can't use ultrasound. You have to use potentially techniques like X-ray CT, which are not cheap. So all I'm saying is you need to factor all of these decisions in. They can all be overcome, but you need to plan them at the start. Yeah, I think those that have already gone down this journey know some of the things that can go wrong. It is quite a challenging journey. The companies that are being successful today have made mistakes. They've learned by making those mistakes and stuck with it, GE included. So you have to, don't make the first mistake the last one you ever try. Otherwise, you'll be behind your competitors. A little bit about what we do, because I'm not necessarily selling a product. I'm here really to help. And we recognize that it's a complicated area and you need advice. And if you go around these stands, you'll get plenty of advice. But if a guy's selling a machine, it's unlikely he's going to recommend an alternative. Okay? I don't have any affiliation to any machine. So I'll tell you how it is, good, bad, or ugly. So at the MTC, we're based in Coventry, we've formed the National Innovation Centre for Net Shape Additive Manufacturing. And it's really a demonstration factory for new technology, particularly in additive manufacturing. So we'll show you the full process. Because when you go around here, you won't see heat treatment. You won't see part finishing. You won't probably see NDT and inspection. These are all the missing bits that the guys don't tell you when you buy a machine. Our capability is the most extensive of any centre in the world. Okay, and you paid for it. Who's the UK taxpayer here? Okay. The rest of you I don't care about. I'm only caring about the guys who pay their tax in the UK. No, I do care about everybody. It's a global industry. But we're here to help. You've paid for it. For God's sake, use it. Okay? We're happy to help. We do design for additive manufacturing. We can make our own powder. We can characterize that powder. We can handle that powder in an enclosed atmosphere to make sure we don't contaminate the powder or kill our employees. We can simulate the process to make it more efficient. We've got a wide range of net shape additive manufacturing processes. We don't have them all, because there's a lot of them, but we have a cross-section. And we can signpost you to other people that have them, who don't have an axe to grind. We're working on in-process inspection and monitoring. One of the big advantages of making parts in layers is you can see every layer as you make it. You can't do that in die casting. You can't do that in normal casting. You can't do that in injection molding. But looking at that layer, you can see what's going on. You can see if there's defects. You can actually measure the part as you go along. So when you get at the end of the process, you've got a report that says the part's got good integrity and it's the right size. There is no other process like that. We're looking at heat treatment techniques, things like hipping to get the properties up, adaptive finishing. At the moment, if you buy an additive manufacturing machine, you'll probably have to have a lot of guys or girls in a workshop polishing and finishing those parts. This puts us at a disadvantage compared to lower cost economies in the East. We're working on new, quick ways of doing NDT metrology so we can measure the parts quickly so it doesn't become a cost burden. I mentioned about the whole process. The bit in the yellow bit in the middle is what these guys outside are talking about, the machines. But you're using powder that gets recycled, particularly in the metals machines. That has to be monitored and controlled. It's the old adage, if you put rubbish in, you get rubbish out. Okay? Everything needs to be managed. The finishing needs to be considered. The part quality needs to be considered. This is what we do, and we help you When we prove it, we don't sell you parts. You go away with the process, and then you apply it to in your company. Other things we do, we commission big bits of kit that are more production orientated. So we commissioned the world's largest electron beam melting machine. This was actually a couple of years ago, and you'll see that on the Arkham stand. It's now what's called the A2XX. When we bought it, it was called the A2WT, standing for wide and tall. So there you go. It doesn't seem like it's very big. It's a 350 by 380 build chamber, which is laughable when you talk about things like casting or forging. But it's 3 times bigger than the predecessor. It takes 200 kilos of titanium to fill it. We process typically 1.5 tons of titanium a week in our machines. So this is as close as you get to production. We've also ordered some new bits of kit. We've got the world's first Arkham Q20, which is the same as the A2XX, but with all the things fixed, we hope. It also has a very nice surface finish, much closer to laser melting. We also have laser melting equipment, Renishaw AM250 and EOS M280. Each has a particular sweet spot. We quite like the M250, very fine detail, good for things like dental implants and medical implants. The EOS M280, it's a workhorse, knocking out components for general applications. I'm coming to the end of the presentation. I've got 7 minutes to go. I'm going to talk to you about what's happening away from traditional additive manufacturing. You might hear at the show this week something called hybrid manufacturing, because this gives us a whole new option. Additive manufacturing is traditionally quite slow. If you buy a laser melting machine, it might only produce 25 grams of part per hour. Yeah, 25 grams, not 25 kilos, 25 grams of part per hour. It is not fast. Even the EBM machine, which is a lot faster, you'd be lucky to get more than 100 grams an hour, okay, for a machine that costs £500,000. So what we're saying is use additive manufacturing alongside other processes. Don't make it a crusade for additive. Be flexible. So by combining additive manufacturing with things like machining, or even making a forging and growing on a feature by additive manufacturing, you get the best of both worlds. So higher productivity, larger part size, improved surface finish and accuracy. It's a big problem in the industry. A couple of years ago, we started a project funded by the UK government called Reclaim. It was actually about repairing parts. So taking aerospace and automotive parts that were worn and growing on material where there was damage, okay? But actually, the application probably is more additive manufacturing. It's repair, but also new part manufacture. So in fact, we built the next generation machine, which was a commercial machine, which has now been supplied to the power generation sector, allows large ground-based gas turbine blades to be repaired automatically. Materials put down by laser cladding, like a welding process. It's inspected, then machined, and inspected again. So you end up with a fully finished component at the end of the process. There's no manual rework at the end of the process. That's where additive needs to go. In fact, in recognition of that work, the guys who helped develop it got an award at EMO. It's a big German machine tool company. I think it was one of the few non-German consortiums to win an award. We just got the latest version of this machine, which we're using over at Coventry, and the latest version of the cladding head, which is developed by a spin-off company called HMT. And if you want to see that head, it's on stand H32. That's the plugs over, okay? The new centre has a vision which will, as new additive manufacturing techniques get introduced, we'll introduce them into the centre. It doesn't matter about the new processes. We will just take out the old process and put the new process in. What matters is the things either side. how we handle the materials, how we finish the parts off, they are going to be common to other processes. We're also working with the research partners. Anybody here from a university? A few. Okay. We need universities to work on the fundamental science. We end up doing a project and saying we don't understand why it does that. We don't have time to look into that. The universities can find that out, and we have some really good universities in the UK. Final couple of slides. The MTC is part of the high value manufacturing catapult, which is one of the 7 centres. And additive manufacturing has been used and being developed across all 7 centres in some way or other. Okay? To try and help coordinate that activity, we've set up a forum. I chair that forum. And if you want to know what's going on, for example, at the AFRC in Strathclyde, contact me. I can signpost you and put you in contact with the guys that are doing the forging work up there. Same with the guys at WMG in Coventry. You know, we need to make sure this set of centres, which is a little bit like the Fraunhofers in Germany, all work together for the best of UK industry.